All right, so let's get into some applications of implicit differentiation. One of the biggest questions that I said we'll be looking at this semester is finding the equation of a tangent line, because that's what the slope of a tangent line, or sorry, finding the slope and equation of a tangent line, because that's what a derivative is. It's the rate of change at a point or the slope at a point, right? So example 7 says find the slope of a tangent line to the circle x squared plus y squared equals 25 at the point 3, negative 4. So now we're not finding the equation of, the equation of a tangent line of a function. We can actually do it of a circle. So let's think visually what's going on here. So if you know anything about circles, this is a circle centered at 0, 0 with a radius of 5 because the format of it, I know that. But the idea is if you think about when x equals 3, here's x equals 3, there's actually 2 points. So we would actually have 2 tangent lines for the graph. Well, we have to be specific about which one we want. And if you look at the point, the one given to us is the point 3, negative 4. So what this problem is asking for is what's the slope of that red line? Notice it's no longer a function because it doesn't pass the vertical line test, but that doesn't mean we can't find the slope of the equation at a given point. So here's the cool thing. We used to find y prime and then plug in the x value. Well, now we're doing implicit differentiation, right? We still solve for y prime, but using implicit differentiation. But in every one of our answers included both x values and y values. So earlier in the semester, we only had to plug in x values. Now we're going to get an answer that has both x's and y's, and we're going to have to plug in both x and y. But that's okay because the points x and y have been given to us. X is 3 and y is negative 4. So if it says find the slope of the tangent line, it's the same as it's always been. That means find the derivative. So all we're going to do is we're going to take the derivative with respect to x of both sides of this equation. The derivative with respect to x of both sides of this equation. Really not that bad of an equation compared to some of the ones we've done either. So let's take a look at it. Well, what's the derivative of x squared? Derivative of x squared is 2x. Variables match. We don't need to worry about x prime. Derivative of y squared is 2y, y prime. The derivative of 25 is 0. Again, just like always, solve for y prime. So I'm going to subtract 2x from both sides. That would give me the equation. Well, let's take a look at it. It would be 2y, y prime equals negative 2x. I'm going to divide both sides by 2y. I'll do some simplification. I see that my 2's simplify there, right? So I end up with y prime equals negative x over y. Well, what do we care about? We care about at the point 3, negative 4. So anywhere I see an x, I'm going to plug in 3, and anywhere I see a y, I'm going to plug in negative 4. So in this case, y prime would be equal to, well, on top we would have a negative 3 over, and on bottom we would have our negative 4. So that tells me the slope of the line, that red line in that picture that we just graphed, is 3/4. So that's what we were able to do. Of course, if we wanted to find the slope of the blue line, we would have to plug in x and solve for y. But when you solve for y here, you would get 2 values. It's actually 4 and negative 4. So we'd be plugging in a different value for y here. But we have to use the one they gave us on the problem. So really cool. We're able to still find the slope of the tangent line or the slope of the graph at that point. It's just now we have to plug in both the x and y values. Same thing on number 8 here. It says find the slope of the graph of x squared minus 9y squared equals 16 at the point 5, 1. Again, if you know anything about your hyperbolas and your parabolas and any of those different shapes, you would know that this shape is a oval because the values, actually this one's a hyperbola is really what this one is, because the signs on x's and y's are opposite and the coefficients aren't the same. So you could look at the graph of this. You can easily graph this on Desmos and see what Desmos gives you. You could see what the graph looks like. There's no need, though, because we're still able to find the slope of the graph without even seeing the graph using our calculus techniques. How do we do that? Again, we're going to find the derivative with respect to x of both sides of this equation. Let's just do it slowly here. Derivative of x squared is 2x. Derivative of negative 9y squared would be negative 9 times 2, which is negative 18. Then you'd have y to the first power, but we've got to remember that y prime equals derivative of 16 is simply 0. Again, we're solving for y prime, so let's subtract 2x from both sides. When we subtract 2x from both sides, on the left we're left with negative 18y y prime. On the right we're left with negative 2x. We divide both sides by negative 18y. Let's do some simplification. Negative 2 divided by negative 18, isn't that 1/9? So when I do that, I'd end up with y prime equals, on top we had a x, and on bottom we had a 9y. Remember, the negatives canceled, so we had a 9y on bottom. So I'm getting y prime equals x over 9y. Where did we care about it? We cared about it at the point 5, 1. So anywhere we see an x, we're going to plug in 5. And anywhere we see a y, we're going to plug in 1. So that would be 5 over 9 times 1. So what's the slope of the line at that point? The answer is 5/9. So we can now find the slope of the graph. We could also find the equation of the tangent line, right? We have a point, we have a slope. We could find the equation of the tangent line. But all this problem did was find the slope of the graph at a point, and notice it's not even a function anymore. This isn't the graph of a function. It is an equation. We could graph it, but it is not a function, meaning the graph wouldn't pass the vertical line test. Pretty cool. Okay. Let's look at example 9 here. This one's going to mess you up a little bit. I want you to be really, really careful with this one. Okay? It says the demand function of a product is given by p equals 2 over 0.001 x squared plus x plus 1. Find dx dp implicitly. Oof, I want you to be really, really careful with this. They want you to find dx dp. This right here says they want you to find x prime. They want you to find x prime. Notice we are taking the derivative with respect to p, not with respect to x. So now the derivative of x squared would be 2x x prime, not just x, because we are taking it with respect to p. So be very, very, very careful on this one. Okay. So I want to look at this. We have p equals, and then we have, look, on the right, why don't I go ahead and write this as 2 times 0.001 x squared plus x plus 1 raised to the negative 1. Are you guys okay with that? And again, I'm doing that so I can use the general power rule. If I find the derivative with respect to p of both sides, the derivative with respect to p of both sides, well, the derivative of p is simply 1. The derivative on the right-hand side would be 2 times, drop the power, so that'd be negative 1. Then we'd have 0.001 x squared plus x plus 1 raised to the power minus 1, so that'd be negative 2. But then we need the derivative of the insides, the 0.001 x squared plus x plus 1 prime. Whew, there it is. Let's think about what the derivative of that inside would be. Well, what's the derivative of 0.001 x squared? Remember, we have to use x primes here. So the derivative of this term right here would be 0.002, because you have to multiply that times the 2, x times x prime. And then plus the derivative of x is x prime, and the derivative of 1 is still 0. So let's clean this up a little bit. On the left-hand side, I have a 1. On the right-hand side, I have a 2 times a negative 1, so that's going to be a negative 2. On top, I'm going to have 0.002x x prime plus x prime. On bottom, because I'm going to move this entire term down to the bottom, I would have 0.001 x squared plus x plus 1 quantity squared. Again, I need to solve for x prime here. So to solve for x prime, I'm going to multiply both sides by that denominator. That's the 0.001 x squared plus x plus 1, both sides. And it's that quantity squared. So when I do that, on the left I have 0.001 x squared plus x plus 1 quantity squared. On the right I would have a negative 2. Well, I'm going to go ahead and distribute that negative 2. So I'm going to do the negative 2 times this and the negative 2 times that. So I'd have negative 0.004 x prime minus 2x prime. Notice on that right hand side I do have an x prime in common, which is what I wanted, so I could factor it out. So this would be 0.001 x squared plus x plus 1 quantity squared, same thing on the left. Factor out that x prime, I'd be left with negative 0.004x minus 2. Divide both sides by that mess, the negative 0.004x minus 2. And I'm left with x prime equals 0.001 x squared plus x plus 1 quantity squared all over negative 0.004x minus 2. Wow. Pretty crazy here, right? That's what it is.